Welcome to this comprehensive presentation on organic chemistry, where we will explore the fascinating world of carbon compounds and their significance in various scientific and industrial applications. Organic chemistry focuses on carbon-containing compounds, excluding oxides, carbonates, and carbides. It is crucial for understanding biological processes, pharmaceuticals, petrochemicals, and industrial applications like polymers and detergents. Organic chemistry is essential for understanding life processes at the molecular level. It forms the basis for the synthesis of pharmaceuticals and the creation of materials like plastics and synthetic fibers, impacting numerous industries. Organic compounds are primarily made up of carbon and hydrogen, though they may also contain other elements like oxygen, nitrogen, sulfur, phosphorus, and halogens. These compounds are characterized by covalent bonding, where atoms share electrons to form stable molecules. One notable property of organic compounds is their combustibility. When completely burned, they typically produce carbon dioxide and water. Carbon's tetravalency, meaning it has 4 valence electrons available for bonding, allows it to form up to 4 covalent bonds with other atoms, including other carbon atoms. This property is key to the diversity of organic compounds, enabling the formation of various structures, from simple molecules to complex polymers. Let's take a moment to review what we've learned about the basic characteristics of organic compounds. Please choose the best answers for these questions to reinforce your understanding. Carbon atoms can connect in multiple ways. Single bonds, found in alkanes, are the longest and least reactive. Double bonds, typical of alkenes, are shorter and more reactive due to the pi bond electron density. And triple bonds, found in alkynes, are even shorter and more reactive. These bonding variations significantly affect the chemical properties of organic compounds. Carbon's ability to bond with oxygen and nitrogen creates various functional groups vital in organic chemistry. For example, carbon-oxygen bonds form groups like alcohols and carboxylic acids, while carbon-nitrogen bonds lead to amines, amides, and nitriles. These bonds significantly influence the reactivity and application of organic compounds. Catenation, the ability of carbon to form chains and rings, is a fundamental property that allows the creation of a wide variety of organic structures, including straight-chain hydrocarbons and cyclic compounds. An empirical formula represents the simplest whole number ratio of elements in a compound. For instance, the empirical formula of glucose is CH2O, indicating a 1:2:1 ratio of carbon to hydrogen to oxygen atoms. The molecular formula, however, shows the actual number of atoms of each element present in a molecule. Glucose's molecular formula, C6H2O6, reveals it contains 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Finally, the structural formula provides a visual depiction of how these atoms are arranged, illustrating the specific bonds between atoms. To calculate an empirical formula, we start by determining the percentage or mass of each element in the compound. We then convert these to moles, divide by the smallest mole value to find the simplest ratio, and adjust to whole numbers if necessary. Let's explore this process with some examples to solidify our understanding. Let's take a look at some examples on calculating empirical formula of a compound. Follow the steps for proper understanding. To determine the empirical formula of a compound with 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen, we first convert these masses to moles by dividing each by their respective molar masses. For carbon, we divide 40 by 12, obtaining 3.33 moles. For hydrogen, we divide 6.7 by 1, getting 6.7 moles. For oxygen, 53.3 divided by 16 also gives 3.33 moles. Next, we divide each mole value by the smallest, which is 3.33, yielding a ratio of 1 to 2 to 1. Therefore, the empirical formula is CH2O. For a compound containing 85.7% carbon and 14.3% hydrogen, we begin by converting these percentages to moles. Carbon's mole value is found by dividing 85.7 by 12, resulting in 7.14 moles. Hydrogen's mole value is 14.3 divided by 1, yielding 14.3 moles. We then divide each by the smallest value, 7.14, to obtain a ratio of 1 to 2. Thus, the empirical formula is CH2. For a hydrocarbon containing 88.9% carbon, we first calculate the percentage of hydrogen, which is 100% minus 88.9%, equaling 11.1%. We then convert these percentages to moles. Carbon's mole value is 88.9 divided by 12, yielding 7.41 moles, while hydrogen's mole value is 11.1 divided by 1, giving 11.1 moles. Dividing each by the smallest value, 7.41, results in a ratio of 1 to 1.5. To convert this to whole numbers, we multiply both by 2, resulting in the empirical formula C2H3. Now, let's assess your grasp of carbon's bonding capabilities. Answer these questions to check your understanding of single, double, triple carbon-carbon bonds and calculating empirical formula. In summary, we have explored the fundamentals of organic chemistry, including the characteristics of organic compounds, the tetravalency of carbon, and the various types of carbon bonds. We've also looked at catenation and how to calculate empirical formulas. These concepts are vital in understanding the complexity and diversity of organic compounds. Thanks for watching. To deepen your understanding of any topic, explore our comprehensive resources, including revision notes, past questions, gamified quizzes, and workbooks. These tools are designed to help you master the concepts effectively and enjoyably,